Good morning, calculus students. This is Miss G. Today is Wednesday, April 15th. And did you catch yesterday my mistake? I didn't know what day it was. Yesterday, I labeled my notes as Monday, but yesterday was Tuesday. So I wanted to correct that. I'm on the right day today. Today is Wednesday. Okay, I know some of you caught that. Too much vacation for me, I think. All right. So today we're going to do section 4.5. We're going to continue in that section. So we're going to talk about the fundamental theorem of calculus. So here's the fundamental theorem of calculus. If f is non-negative, that means the graph of f is above the x-axis, and continuous on the closed interval ab, then the integral from a to b of lowercase f of x dx is equal to capital F of b minus capital F of a, where capital F is any function such that capital F prime of x is equal to lowercase f of x for all x in AB. Now that's a little confusing, but I'm going to show you an easier explanation of that. That's the official math calculus definition of the fundamental theorem of calculus. But here's a simpler version, okay? We have the integral from a to b of lowercase f of x dx. What we're going to do is find the antiderivative. You've been integrating, so you know how to find the antiderivative for this function. That's what capital F of x is. It's the antiderivative. And a and b represent numerical values, and they will be in the problem. And what you do is after you find the antiderivative, you plug b in first. You substitute b into the antiderivative first, and then you substitute a in the antiderivative after that, and you subtract those two values or those two numerical values that you get. And that's your answer. And what does that give you? That gives you the area bounded by the curve, the x-axis, and vertical lines at x equals a and x equals b. It's like we did yesterday, except we did it geometrically yesterday, and today we're using calculus. In fact, these are the same two problems you did yesterday geometrically because they were made up of line segments yesterday. And so I'm going to show you that we can do them also using calculus. So here's yesterday's problem. The integral from 0 to 2 of 2x dx. You find the antiderivative like you did yesterday. Remember, you add 1 to the exponent, you get 2, you divide the coefficient by the new exponent, you get 1. So the antiderivative of 2x is x squared. And then you put a little symbol like this, which means now we're going to evaluate it. Some people make that a straight line. I put little brackets on it. And then you copy these numbers over here, 0 to lower limit, upper limit. And then you plug the upper limit in, the one that's located at the top of the integral sign. You plug that into x first, and you get 2 squared. And you're going to subtract what you get when you plug the lower limit in, which is the one located on the bottom of the integral sign, and that is 0 squared. And what you end up with is 4 minus 0 when you work it out. And that's what we had yesterday for the answer to our first problem. And that gives us the area bounded by this curve, the x-axis, and vertical lines at x equals 0 and x equals 2. Although there wasn't a line at 0 yesterday because 0 was right on the graph. Okay. Now, this is the other one we did yesterday. The same function, 2x, but we were going from 1 to 2. So we still find the antiderivative, the integral from 1 to 2 of 2x dx. Find the antiderivative of 2x, that's x squared. Recopy these numbers over here, 1 to 2. Put your little bracket that knows we're going to evaluate it. Plug in 2. We get 2 squared. Minus, plug in 1. We get 1 squared. Subtract, we get 4 minus 1, which is 3. And that was the answer to the second problem we did yesterday. Okay, so yeah, we did these with geometry yesterday. Notice that there's no plus c's, like when we integrated indefinite integrals, the ones that didn't have the numbers on the integral sign. When we were done with the antiderivative, we put in a plus c. There are no plus c's in the answers to these definite integrals. If you put one in, if you put it in x squared plus c, then you would end up putting it in the first half and then subtracting it out in the second half. So it wouldn't be there anywhere. So just know that there's no plus c's. We're going to get numerical answers for these. Okay, now let's see what I did. Okay, so now what I did was I did some more problems so you could get the hang of it. So let's see what we've got. All right, so here's the first one. The integral, number 3. The integral from 1 to 3 of x cubed dx. So what are we looking at? Let's see. We're looking at the cubic function, y equals x cubed. Here it is. And we're integrating it from 1 to 3. So we're finding this area bounded by the curve, the x-axis, and vertical lines at 1 and 3. What do? We find the antiderivative of x cubed, which you now know is 1/4 x to the 4th. Copy these numbers over here on our little bracket. Plug the 3 in first, so we get 1/4 times 3 to the 4th power minus 1/4 times 1 to the 4th, and then just work it out. 1/4 times 81 minus 1/4 times 1, 81/4 minus 1/4, and we get 80/4, which is 20. So 20 square units is the area bounded by the curve and the x-axis and those vertical lines. You see, we can't do this one by geometry because one of the boundaries is a curve. It's not a line segment. So that's the great thing about calculus. It helps us find areas involving curves. All right, let's look at another one. It's worded a little differently. Find the area of the region bounded by the x-axis and the graph of f of x equals x squared minus 1 when x is between 1 and 2. And that's giving you the limits of integration. That's what that is going to do. So I would always graph this, so I'd like to see what I'm looking at because sometimes a picture is worth 1,000 words. So I graphed the x squared minus 1. Here it is. And I'm putting vertical lines at my boundaries, x equals 1 and x equals 2. 1 is already on the curve, so I can't draw a vertical line from 1 to the curve. So I just make sure I note that that's on the curve. And then I draw a vertical line at 2. And then I shade from 1 to 2 underneath the curve. So what I'm finding is this area between the x-axis, the curve, and 1 and 2. All right, so now you have to set up the integral giving that information, but it's not too hard. It's just the integral. Then put your function, x squared minus 1, with a dx, don't forget the dx, and then put your limits of integration from 1 to 2. And then we just find the antiderivative. The antiderivative of x squared, which is you're integrating, x squared, you get 1/3 x cubed. And the antiderivative of 1 is x, and we bring down our minus sign. Then, copy over the limits of integration, plug in the upper limit, which is the one located at the top first, and then plug in, so we plug in 2 first, then we plug in the 1. So we plug in the 2, we get this expression, we plug in the 1, we get this expression, we subtract, we're going to work it out. We get 1/3 8 minus 2 minus 1/3 times 1 minus 1. Multiply the 1/3 times 8, we get 8/3. I converted the 2 to an equivalent expression as 6/3. And I got 8/3 minus 6/3, which is 2/3. And I have 1/3 minus 1, 1 being 3/3, which gives me negative 2/3. And my final answer is 2/3 minus negative 2/3, which is 4/3. Okay. All right, so I hope you followed that. Let's look at another one. Yeah, let's look at another one. Okay. All right. This one is a little more complicated, but you know how to do u/du substitutions. So here's our integral. We're integrating from 0 to 1, 2x plus 3 to the 3rd power. And now we have a function within a function, so we're going to do a u/du substitution. So u is 2x plus 3. The derivative of that, 2x plus 3, is 2 dx. We don't have a 2 in front of our parentheses here, so we picked up a 2 we don't want, so we need a 1/2 in front of the integral. Now I'm going to integrate u cubed du. I'm not putting any limits of integration right now on my integral sign because later on we'll learn that when we're integrating with respect to u, we would have different limits here. But once we put the x's back in at the end, I'm going to put these limits back in. So I'm just leaving them off temporarily. And now I'm going to integrate u to the third power. So that gives me 1/4 u to the fourth. I have my 1/2 out here. Remember, there's no plus c's in the problem. In these definite integrals, I'm going to get 1/8 u to the fourth. And now I'm going to put the x's back in. 2x plus 3 goes in for my u to the fourth power here. And now copy those limits on my little evaluate sign. And we're going to substitute in the 1 first and the 0 second. So I'm substituting in the 1, substitute in the 0, and work it out. So this gives me 5 to the fourth. This gives me 3 to the fourth. And I end up with 625 eighths minus 81 eighths, which gives me 544 eighths, or 68 square units. Okay, I think I have one more of these to do. Let's see. Find the area of the region. And this one, they drew the region for you, and they give you the function. So here's the function, x minus 2 over x. That's this function. And we're looking at it from 2 to 4. So we have to set up the integral. So it's the integral from 2 to 4. And then we write our function with a dx. Now, if you recall, when we integrated before and we had a monomial, one term in the denominator, we split this up. So I'm going to split that up like we did before. So I'm going to have x over x minus 2 over x dx. From 2 to 4, we're integrating that. And I'll simplify it. And I'm going to split it into two integrals. You don't have to, but I think it makes it easier to see in this particular problem. So x over x is 1. So I'm integrating from 2 to 4, 1 dx. Minus, this is 2 over x, which is really 2 times 1 over x. And 2 is a coefficient, so I just put the 2 in front of the integral sign. And I'm integrating 1 over x from 2 to 4 dx. Now, the antiderivative of 1 is x, and we're going to integrate that from 2 to 4. I bring down my minus 2 coefficient, and I integrate 1 over x. I hope you remember, I know it's been a while since before vacation, but the integral, the antiderivative of 1 over x is the natural log of the absolute value of x. I hope you remember that. And then we're going to integrate this from 2 to 4. So let's see what happens. Let's do the x first. So we plug in the 4 first. We plug in 2. We subtract 4 minus 2. We get 2. Okay, so we're done with the x. Minus, bring that sign down. Let's look at this. We plug 4 in for x. And we don't need the absolute values because 4 is positive. That's why I took the absolute values off of there. So I have 2 ln 4. Minus, plug the 2 in, 2 ln 2. Again, we don't need the absolute values here because 2 is positive. Then I simplify this. I get 4 minus 2 is 2, minus 2 ln 2, and then don't forget to distribute this negative here as well. So that becomes minus a negative, and that's plus 2 ln 2. And I did give you one like this for homework. And I do believe that the back of the book just puts this in decimal form. So you can just plug this into your calculator and it works out to 0.6137 or 6,137 10,000ths. And that's square units for that region, the area of that region. Okay, so I have a few problems. I hope you followed this. This is the hardest one of all. Don't get nervous. And so the homework is section 5.4, page 348, numbers 9, 11, 15, 17, 19, and 21. And they're all just like the problems that I just did. If you have any questions on them, please email me and I will do them in my next video so you can see if you get stuck on any of these, okay? Have a great day. All right, take care.